everyone, this is a video to go along with sections 4.3 and 4.4. Alright, in these sections we're talking about a few more quadrilaterals, the rectangle, square, rhombus, and trapezoid. Okay, so one of the things I want to do is have you do an exercise to compare the relationships between all of the quadrilaterals we've talked about so far. So we're going to go through the definitions, but also we need to review one way to visually organize these relationships, and that is Venn diagrams. This is back in section 1.1 in the textbook if you wanted to review that. But you may remember some common Venn diagram pictures would look like this. So you have sort of a rectangle, and then inside you usually have a couple of overlapping circles. So usually the rectangle represents the context of the problem. So for our example, we're talking about quadrilaterals, so I might use the rectangle to represent all quadrilaterals. Then inside we've got these different circles which could represent some sets of different types of quadrilaterals. In a non-mathematical context, maybe we have, this could be like LBC students, and maybe the circles represent freshmen and seniors. Okay, so in this case, the overlap represents that there are some freshmen who are also seniors. Right, so if that doesn't seem to fit the scenario or make sense, then we can draw these circles not overlapping. All right, so if we have overlapping circles, those are intersecting sets, and things in the middle would be things that are part of both sets. If we don't overlap the circles, okay, maybe we want to show that freshmen and seniors are completely different, and those are called disjoint sets. So we would draw those not overlapping, and that would show that they don't share any elements in common. Another type of relationship would be if there's a set inside of a set, so like a smaller category. So let's say, let's say we're talking about food. Okay, that could be like our larger context, and maybe we have a set of green food. Okay, well then broccoli would be considered a subset of green food. Alright, and I know we have maybe some related broccoli-like plants that are not green, but your traditional broccoli, all of those plants would be green, so that would be a subset inside of there. Okay, and so then you'd have one circle inside of the other. Alright, if we wanted to describe these relationships verbally or maybe mathematically, we would, in the first situation, if we have intersecting sets, then we would say that there are some things that are in both sets. Okay, if the sets are disjoint, then there are no elements in common. Okay, so something couldn't be in both of those sets. And in this last case, anything inside of the smaller set is also part of the larger set. Okay, so we would say that all things that are in that smaller set are also in the larger set. A mathematical example for that one would be squares and rectangles. So we would say all squares are rectangles. Okay, and we would have the inside circle be squares. There's squares. Okay, and then this outer circle would be rectangles. Okay, and we could also say if a shape is a square, then it is a rectangle. Okay, so let's look through the definitions. You can read these on your own as well from the textbook, but just to review, we've talked about quadrilaterals. They're polygons with four sides. Parallelograms are quadrilaterals in which both pairs of opposite sides are parallel. Okay, so we have parallel sides here, parallel sides here. Okay, and then notice they're also quadrilaterals, so that carries some more information as well. We didn't repeat the fact that they had 4 sides, but that's built into the definition. Kites are quadrilaterals with 2 distinct pairs of congruent adjacent sides. Okay, so we have 2 sides congruent to each other, they're adjacent, and then the other 2 are congruent to each other, but not to the first pair. Okay, so they're definitely different length. And then notice those are, kites are also quadrilaterals. Okay, new definitions. These may be a little bit different than how you've seen these shapes defined before, so we certainly know all of the typical facts about them, but we're just going to have those facts somewhere else other than the definition. So, for example, we know squares still have 4 right angles, but that would be proved later as a theorem or a corollary, but it's not going to be part of the definition. Alright, so here are the textbook definitions. A rectangle is a parallelogram that has a right angle. Okay, so as long as it is a parallelogram and it has one right angle, that's sufficient to make it a rectangle. And then we can prove all of the other facts from there. Okay, things that we know about rectangles. A square is a rectangle that has 2 congruent adjacent sides. Okay, so it's a rectangle, and it has 2 congruent adjacent sides. And of course we do know that all 4 are the same, but that's something that we could prove based on this definition. Right? And then notice because it's a rectangle, that means it's a parallelogram, that means it has a right angle, and so forth. A rhombus is a parallelogram with 2 congruent adjacent sides. Okay, so these are like your diamond shapes. Here's one way to draw these. Okay, and since it's a parallelogram, all the sides are parallel. Okay, and we have 2 congruent adjacent sides. Right, another way to draw it is sort of sideways. This shows a little bit more clearly that it's a parallelogram. If you draw it like this, and still with 2 congruent adjacent sides. Okay, so notice my drawing sort of looks a lot like the kite one, but the difference here, we can prove that all 4 sides of the rhombus are the same, they're congruent, and what's different from a kite is also that this is a parallelogram. Kites are not parallelograms. Right? So if you have 2 congruent adjacent sides and not a parallelogram, okay, that's going to fall into the kite category. But if it's also a parallelogram, then that's going to drag the other 2 sides into also being congruent. Because remember, in a parallelogram, we know that opposite sides are congruent. Okay, so the top would be congruent to the bottom here, and the right would be congruent to the left. And then the last one, finally, a trapezoid is a quadrilateral with exactly 2 parallel sides. So the other 2 are not parallel. Okay, so here's here's one version of a trapezoid. Okay, and then these 2 sides would be the ones that are parallel based on how I've drawn it. Sometimes you've seen the ones that are symmetric. Okay, those are isosceles trapezoids, where the left and right sides are the same length. And we could probably draw some non-standard trapezoids as well. Okay, so see if you can draw a Venn diagram to represent the relationships between all of these different shapes. Right, so start out with a rectangle to represent quadrilaterals, okay, because all of these shapes are quadrilaterals. And then you usually just kind of label, like off to the side or in the top corner or something, the name of the rectangle or the circle. Another hint would be the squares and rectangles relationship. So since we know that all squares are rectangles, okay, then when you draw your rectangle circle, okay, then you'd have a circle for, now you can modify this if you want to, but if you drew a circle inside the rectangle one for squares, then that would show that all that all squares are rectangles. Okay, so what you wouldn't have a circle like this, because this would imply that there are some squares that are not rectangles. All right, and then similarly, you wouldn't put the squares one surrounding rectangles, okay, because that would mean that every rectangle is a square, and that's not the case. Okay, so see if you can finish this. So draw other circles in here. They can overlap if needed. They can be disjoint. Okay, they can be inside of each other. But what is the best way to show all of these different relationships? All right, another concept in this section is the Pythagorean theorem. So on the right and at the bottom, maybe the way you've seen this previously. So we know that for a right triangle with a hypotenuse, which is the longest diagonal side of length C, okay, and that's also the one across from the right angle, and legs of lengths A and B, we know that A squared plus B squared is C squared. Okay. And then on the left there's an example. So if we know legs of length 3 and 4, and if we know that this is a right triangle, okay, then we would be able to show that the hypotenuse is 5. Okay, and notice that this does fit the relationship. 3 squared plus 4 squared is 5 squared. Okay, so we have 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, and that's 5 squared. All right, and then there are lots of different proofs of this theorem, so we'll get to a few more formal ones a bit later in the textbook, but here's just a really quick visual. I hate to call it a proof, either a picture proof or just an illustration to convince you of the truth of this theorem. But if you look at the actual geometric meaning of squared, okay, when we say that something is squared, like 3 squared, it's called that because it is connected to the actual figure of a square. Okay, so squaring 3 means to make a square with side lengths of 3. Okay? And then if we look at the area in square units, okay, notice that it's the area is 9 square units, or you can have 9 little squares in that area. All right, so visually what we're saying is that if you draw squares with the legs 3 and 4 as the side lengths, then their areas are the same area as if you draw a square with a side length of 5. Okay? And then visually, if you wanted to show this, you could even leave this larger square blank, and you could show that it's possible to shift all of these little squares, okay, from the 2 smaller ones over to fill in the larger square. All right, so why is this Pythagorean theorem in this section? Well, a lot of times we use it to find lengths of diagonals or sides of shapes. It's a convenient way to find distances in geometric diagrams. So here's a simple one. What's the length of each side of a rhombus whose diagonals measure 10 centimeters and 24 centimeters? All right, so as you read through this textbook section, there are lots of different facts about the plural of rhombus is rhombi. Okay, so there are lots of facts about rhombi that I haven't mentioned in this video, but one of them is that the diagonals bisect each other. So I would know that if one of the diagonals measures 10 and the other is 24, then those each get bisected, and then we would have half of them would be 5 and 12. Okay, so notice now we have a right triangle formed by 2 halves of the diagonals, the 12 and the 5. Okay, and we can also show using a proof that that is a right angle there. And now we could use the Pythagorean theorem to find the length of one of the sides of a rhombus. All right, so we would have the equation 5 squared plus 12 squared is c squared, and that's 25 plus 144, and that's 169. And then if you square root that, you get either positive or negative 13, And since this is geometry and C represents a length or a distance, we always go with the positive answer. Okay, that's the ruler postulate. A length has to be a positive number. So C would be 13. Right, and then we also know that rhombi have 4 congruent sides, so now all 4 sides would each be 13 centimeters. Here's another one. This one doesn't work out with an integer answer, but if we looked at a softball diamond, which is actually a square, and we know that the distance along the base paths is 60 feet, then we can use the Pythagorean theorem to find the distance from home plate to second base. So since this is a square, and we have a right angle, we have a right triangle, so we'd have 60 squared plus 60 squared is c squared, and if you square and add those together, you get 7,200. Alright, and then when you square root that, if we want a distance in feet that's rounded, we could give a decimal answer, but I'd also like to talk about simplifying square roots just as a quick review. Right, so we need to square root 7,200. Okay, so the gist, you want to try to break this down into as many perfect squares as possible. Okay, so one of the rules for simplifying, you don't want a perfect square factor of the number inside the square root. So one that sticks out to me would be 100. So I can make this square root 72 and square root 100. And I chose 100 because I knew that that could easily be square rooted to get 10. 72, I would do the same thing. So lots of factors of 72, but think of one that's a perfect square. And so you might go with 9 and 8. Okay, and then the square root of 9 is 3. 8, you might choose 2 and 4. And I'm doing square root since it's square root of 8. Okay, so that would be square root 2 times square root 4 is square root 8. And then 4 can be square rooted, that's 2. And then 2 cannot be square rooted. It is a prime number, and there are no other perfect squares that are factors of 2. So we stop this process anytime we get, or anytime we can actually take the square root. So that's sort of like the end of a branch, or anytime we can't go any farther with simplifying. And then you just multiply to put it back together. So this would be 10 times 3 times 2 times square root 2. And that would be 60 square root 2. Okay, also in this section are cyclic quadrilaterals. So these are ones where all of the vertices of the quadrilateral lie on the circumference of a circle. Okay, so here's an example on the left. This is a rectangle, and all of its vertices are on the circle. Okay, so that would be a cyclic quadrilateral. On the right, here's an example of something that's not a cyclic quadrilateral. Okay, only 2 of the 4 vertices are on the edges of the circle. This is a true statement. All rectangles are cyclic quadrilaterals. However, the next one, I put this in here because it was in the book, but going through this I realized that this is actually a false statement. Okay, no rhombus is a cyclic quadrilateral. So that is not true. So see if you can think of a counterexample. There is one specific type of rhombus. Okay, it's also got to be another, we can give it another shape name. Okay, so if the rhombus is also a what, then that could be a cyclic quadrilateral. Alright, the key to decide whether or not a shape can be cyclic, you have to see if the diagonals can all intersect at a point that is equidistant from all 4 vertices. Right, so let's use this rectangle as an example. If I draw in the diagonal AC, right, notice that since the vertices are on the circle, okay, then we've got a chord that runs through the circle. All right, and then I've got another one from D to B. Now I know for a fact that the diagonals of rectangles are congruent, all right, so I've got two congruent diagonals there. And I also know they bisect each other, so we've got, so for shorter line segments here that are all equidistant from the four vertices, okay, so what we can do is treat those as radii of a circle. Okay, and the gist, we haven't gotten to circles yet, but basically we can get a circle through 3 points like this. So here I've got 4, and since A, B, C, and D are all equidistant from this purple center point, then I can just make that the radius of my circle, and it'll work out to get a circle through those 4 vertices. All right, this example from the book, we've got a cyclic rectangle, and we're doing another Pythagorean theorem problem, so this one's a pretty easy one, but we know that AB is 8, and the diagonal DB of the rectangle is the diameter of the circle, and it measures 10. Okay, and since we know it's a rectangle, we know that this is a right angle, so we can use Pythagorean theorem to find this missing other width of the rectangle. Okay, so if you work that out, you'll see that that equals 6. Right, and then the perimeter of the rectangle, you would add up 2 times 6 and 2 times 8. All right, altitudes of trapezoids. So this is we've talked about altitudes before, but not for trapezoids. All right, so just a review of the definition. A trapezoid is a quadrilateral with exactly 2 parallel sides. We consider those parallel ones to be the bases. So in this diagram, it's HL and JK that are parallel to each other. And those are called the bases even if the trapezoid is oriented differently. So if I were to stand it up on end like this and have these be parallel, then those would still be the bases. Then an altitude is a line segment from one vertex of one base perpendicular to the opposite base or to an extension of the base if needed. So for example, I could start at vertex H and drop a line segment perpendicular to base JK, and that's an altitude. I could also start at K and drop a line perpendicular to HL, and it's going to be not hitting HL, but it will hit an extension of HL. So if I extend this and make this perpendicular, okay, then this length from K up to the extension of the base is the altitude. Okay, so we have 4 altitudes. Here's another one from L to the base, and then the 4th would go from J up to an extension of HL. Okay. This altitude is also called the height of the trapezoid, and all 4 of those would be the same length. Alright, I've just chosen a couple proofs to work from this section. There are others in there, and there are also some that are left for you as exercises, but here are 2 of the ones that I thought were a little more complicated and that were missing some of the details in the book. So the first one is on page 205, and we want to prove that the base angles of an isosceles trapezoid are congruent. Okay? So unlike an isosceles triangle, which has 2 base angles, an isosceles trapezoid actually has 4 base angles. Okay, so let me draw this. And we'll go with the lettering in the textbook example. So we've got isosceles trapezoid RS TV. Okay, and the part of the definition of an isosceles trapezoid is that the 2 legs are congruent. So we can assume that RV and ST are congruent. All right, so let's write a given statement. So we are given isosceles trapezoid RSTV. Okay, and we want to prove, so we've got 2 angle pairs. We want to prove that R and S are congruent, and also that V and T are congruent. Okay, so first of all, okay, we start with the given again, isosceles trapezoid. Trapezoid RSTV. All right, and then based on the definition of that, I know that RV is congruent to ST. Definition of isosceles trapezoid. All right. Now we need auxiliary lines in here to help us out. So we're going to construct the altitudes. Okay, so I'm going to construct the altitude RY and the altitude SZ. Okay, so I can say that in words. Okay, construct RY perpendicular to VT and SZ, maybe better put a little, let me straighten out that Z. Okay, construct SZ perpendicular to VT. All right, and a reason for that, if you flip back through to some of the initial postulates, we have postulate 6 to construct the line that is perpendicular to a given line. So we're constructing ones perpendicular to VT from points not on the given line, so from R and from S. Okay, so that's postulate 6. Then I also know that RY and SZ are congruent. And we have a theorem that says that. There's one that says that parallel lines are everywhere equidistant. Okay, so I probably should have stated in here back with definition of isosceles trapezoid. Let me add this in. I know that RS is parallel to VT. Okay, so they're everywhere equidistant, meaning if I were to connect any point on RS, and if I were to connect it down to VT in a perpendicular manner, then the length of that line segment would match. Okay, so all of these would be the same length. All right, and that theorem is 4.1.6. Okay, so those are congruent. All right, I'm going to use hypotenuse leg as a reason to show that these two little triangles are congruent. If you did not want to go with hypotenuse leg, it's a slightly longer proof, but you could still get there using one of the other reasons for triangle congruence. Okay, but the fastest way to do it is hypotenuse leg. So the next thing is a triangle RVY is congruent to triangle STZ. And that's hypotenuse leg. Okay, and then that would lead us to angle V and T being congruent. Okay, and that's CP, CTC. Corresponding parts of congruent triangles are congruent. And then all that's left is angles R and S. Okay, so I'm going to refer back to a simplified diagram before we drew the auxiliary lines. So if I get rid of these and just look at the initial diagram of the trapezoid, right? I'll continue on with the proof. So now if you look at, oops, let me get rid of y and z too. Okay, if you look at angles R and V, notice we already stated previously that RS and VT are parallel, so that would make angle R and V consecutive interior angles. Okay, so we know that R and V are supplementary. Okay, and we also similarly know that S and T are supplementary. And the reason for that is theorem 2.1.4. And that one states that if two parallel lines are cut by a transversal, so here the legs are the transversals, then the interior angles on the same side of the transversal are supplementary. All right, and now I can jump to the fact that that R and S are congruent. All right, and why is that? Well, we have a theorem 1.7.3, and that one states that if two angles, okay, so in this case R and S, if two angles are supplementary to the same angle or to congruent angles, okay, so R and S are supplementary to V and T, which I've already established to be congruent, okay, then the conclusion is that these angles, R and S, are congruent. All right, so now we've shown that R and S are congruent and V and T are also congruent. Okay, one final proof from this section. This one is from page 208. If three or more parallel lines intercept congruent line segments on one transversal, then they intercept congruent line segments on any transversal. Okay, so this one's a bit longer to prove, but here's the gist. In this example, in this figure, our three parallel lines are going to be A, B, and C, and let's suppose that they intercept congruent line segments on transversal T. Okay, so what we mean by that is that AB and BC are congruent. Okay, so it's the three parallel lines that are making those congruent segments. Okay, then the conclusion is that A, B, and C, those lines, will form congruent line segments with any transversal. Okay, so say I add in this new one M and cut that across lines A, B, and C, then I can prove that DE and EF are the same length. Not necessarily the same as AB and BC, but they should be the same as each other. Okay, and that's true for any transversal. So if I were to go farther down and draw another one, okay, then I'd have two more congruent segments. Okay, or maybe I want to go down the middle here, okay, and then these guys, let's see, these ones, okay, would be congruent. Okay, so how do we prove this? Well, from the diagram, we're going to start with some auxiliary lines. So we're going to draw DR, and R is on B, okay, and we're going to draw that so that it's parallel to AB. Okay, so these guys are parallel, and then we're going to draw ES that's also parallel to AB. Okay, so all four of these are parallel. Okay, or three, AB is the same line. Okay, so then what we've formed is a couple of parallelograms. Okay, so we've got AB, RD, and we've got parallelogram BC, SE. Okay, because remember that we already showed that these three lines are parallel. That was part of the given information. All right, so now what do we know about parallelograms? Well, we know that their opposite sides are congruent to each other. Okay, so I know that DR and AB are the same. And we already assumed that AB was the same as BC. And now in this bottom parallelogram, I know BC is the same as ES. Okay, so by transitive property, I know that DR and ES are congruent. Okay. Now I also know that if I look at M as a transversal of DR and ES, okay, and M is the transversal, then I can also say something about some of the angles. So I'm going to focus in on these little two triangles here, and I'm going to try to show that those are congruent. Okay, so if you look at this angle and this angle, okay, that's angle RDE and SEF. Okay. And those are corresponding angles, so we have a postulate or a theorem, I can't remember which, that says that those two are congruent. Right? And then similarly, I know that M is a transversal of B and C. Okay, so I can focus in on, I'll put these in red, okay, angle RED and angle SFE. Alright, and those are also corresponding, and I can show that those are congruent. Okay. So now by angle, side, those two little tiny triangles are congruent. Okay, so triangle red is congruent to triangle SFE by angle, side. And then I can use CP-CTC to say that DE is congruent, DE is congruent to EF. Okay, and then that's what we were trying to prove. Okay, we were trying to prove that these new intercepted line segments are also congruent to each other. Alright, so that's sort of a lengthy proof, and that summarizes just some of the key ideas from these sections. I did skip quite a bit in this video, so make sure you go back through, read through the theorems, any facts that we know about rectangles, squares, trapezoids, and rhombi, and read through some of the proofs that are more detailed and explained in these two sections.